So hello everybody, I'm going to talk about Gillian, a multi-language platform for symbolic testing and verification. This is very much joint work with my co-authors. Jose used to be at Imperial and has just moved to an academic job at the Technical University in Lisbon. Petter is on the chat, so if you please ask questions, you can ask questions such as, what on earth does she mean here? Or maybe some more technical questions on something that I happen to say if you want more details. But he is extremely proficient on this work, and so will be able to answer your questions very well. And maybe the interesting ones we could also talk about at the end. Sasha is a PhD student with me. So I've been working on Gillian the first publication was this year in PLDI. This work is for real-world languages. It's working with JavaScript and C. And even though I've only just published, I've actually been working on JavaScript verification since 2012. So there's a long sort of lead up to now, no, we're not just doing JavaScript verification, we're doing verification for many target languages. And the ones we're exploring at the moment is JavaScript and C. We've done more mature reasoning on JavaScript just exactly because of this history, but we're catching up fast with the C work. So Gillian does unified symbolic analysis. And in particular, it does whole program symbolic testing, verification, and automatic compositional testing. So many of you probably have come across symbolic execution, which is a technique for doing certain type of analysis. And the idea is that the coder puts in first order assertions about symbolic inputs and outputs and assertions to help the tools along the way. We do it in a slightly different way from others that are aiming fast and quick to industry. Our philosophy is we've got unit tests. We all know what unit tests are, and we want symbolic tests. We want to understand what does it mean to do more with the testing as one is writing the program. And probably this is influenced by the fact that we're actually doing a lot of work on full verification. So we really don't mind trying to work out what either a specialist developer or a more general developer might be able to cope with in terms of annotation versus what they might not want to do. So with symbolic execution, we have these first order assertions. We have bounded correctness guarantees. We're not doing any sort of invariance of loops at all. We just unroll up to a bound. And we may hit the bound and stop. So we're correct up to a bound, or we're not correct. And there's a concrete counter model that says exactly why you're not correct. So in our world, we've got the symbolic tests. We run that symbolic test, and if it's not going to work, you're going to get a counter model, which is a unit test, a concrete unit test telling you what's going on. But there's been a lot of work in industry on symbolic execution, and we're part of that story. There's much less work going on with respect to verification. They're just starting. Amazon seem to be putting quite a lot of effort into full verification right now. But I think even they would admit that it's not ready yet. It's at the level of we can do some things, not that it's a tool that can be used in general at the moment. And here, for those of you who know, we're doing analysis based on separation logic. So what this means from the point of view of the verification is that we're compositional. We can have specifications of functions and then have a program that calls those functions and builds up layers of specification. And we get functional correctness guarantees. They can be as strong or as weak as you like. So it could be a shape of a list, or it could be an actual mathematical description of a list. And we get failing symbolic traces if we can't do the verification. And then finally, we've got automatic compositional testing based on bi-abduction. And this is breakthrough work that's come from the Facebook Info team, led by Pete O'Hearn, that also was the inventor of separation logic. And there, the point is, no, the developers haven't time for any sort of annotation. Really make the annotation absolutely as lightweight as possible and do everything automatic. That's fine, but of course one is doing much more lightweight analysis than if we were allowing more annotation by the developer. And there they get bounded correctness specifications or lightweight bug specifications describing why you found a bug. And the lightweight in the sense it's memory overruns, buffer overflows, that sort of thing. It's small things, because the job is for the general developer inside Facebook, what does it mean for the info tool to give back lightweight information that they can act on, rather than a deluge of information that's too difficult for a general developer to cope with. So we're working with Gillian. Gillian is this platform. We call it a platform because it is meant to be for many languages. And its infrastructure is that it's based on an intermediate go-to language we're calling GIL for general general intermediate language. And then Gillian comes from GIL. It's an intermediate go-to language that's very sort of normal technique for people doing building analysis tools, but it's not normal in the sense that it's parametric on the memory model of the target language. That's something that we do. We have built a first-order solver powered by the Z3 theorem prover. And all these sorts of tools and platforms call something such as the Z3 theorem prover. There are other options. And they've all got to do something to move from the analysis they're doing to the Z3 theorem prover. I would say we're not expert in Z3 theorem proving, and we're not expert at that level, but I actually we're doing a pretty good job in getting this first order solver to work. But I think that's actually, we're minimal with respect what we do with Z3, and very much we do as much as we can ourselves. And part of that reason is because we're actually not specialists in this world of the Z3 theorem prover. So I think other people might make other choices to us there. And we have modular analysis of symbolic execution, abstraction, and bi-abduction. And this is us. We don't know people that tools that do this, starting off from a core symbolic engine. And the way we instantiate Gillian is we have to give information about the memory model of the target language, and we have to give a compiler from the target language to the intermediate go-to language. The memory models comprise, we have a concrete memory model and a symbolic memory model. The concrete memory model is used for testing, and in particular testing the compiler here. And the symbolic memory model is used for the analysis. And there are some tools that, for example, start off with the concrete memory model and automatically build up to get to the symbolic memory model. We are not doing that. We are purposely keeping them separate. And the reason for that is that we're really finding ourselves doing lots of optimizations by being able to work directly with this symbolic memory model. And we need a trusted compiler from the target language to GIL. And what I mean by this, the compiler must preserve the memory model on the nose, because the whole point is that the analysis is about the memory model. And it must preserve the semantics. And what's really going on is control flow at the target language is becoming control flow given by a simple go-to language. So we're not doing very much at all in the compiler, except for to make it this Oracle-like thing. We have example instantiations. So there's Gillian while that I actually like being in this place. It's the tiny language for the theorist. And it's used for teaching and for experimentation. So in particular, I teach a 4th-year course mainly on separation logic, but we also talk about Gillian. And in particular, that 4th-year course, and it's an MSc course, the next year, they're going to be the code developers inside the tech companies, especially in London, where I am. So actually, if I can get this information to the undergrads, I'm not far off getting it to the code developers. So obviously, I've got a learning curve to do that, and I haven't, I've still got a long way to go, but at the same time, it's the learning curve that I am doing. I also like it very much for experimentation. I don't need to do a whole compiler from a target language to GIL. I can work with a fragment of the real world language in order to begin to, for example, understand the abstractions associated with how I want to reason about this target language. One thing that was said at the beginning was that I've done some work on concurrency. So in the concurrency, I'm doing nothing on concurrency in this talk. And I do want to bring in concurrency, and I can experiment with this while language. The real world languages that we've done are JavaScript and C. I'll be talking mainly about JavaScript only as an illustrator today. We've also done C. The reason why I'm not talking about it is the block offset memory model is complex. So it's quite difficult to get the ideas across just from by working with C. For those of you who know, I'm working with the ComCirc compiler that's verified in the Coq theorem provers. So it's very trusted. And we found bugs in, for example, the data structure library Collections-C. We've been mainly concentrating on symbolic testing in the C world at the moment. We've got Gillian JavaScript, and there's definitely, we've got a different memory model going on. It's an extensible object memory model, not the block offset memory model of C. That's why we purposely chose these 2 languages, because their memory models were so different. And I'll be talking about this further in the talk. And Sasha's just starting on Rust, because he wants modern language, not C, which I think is a totally reasonable choice to make. And I love the idea that he's doing that. And for example, he's working on Gillian Rust, but he can start with a tiny little while version of the Rust-like language to experiment, and he can build up slowly and work out what he needs. And that in parallel, he can do this macho compiler from Rust to GIL. So this is where we're at the moment. Now, I'm not expecting you to know this formalism. I'm a theorist, so I've put the formal stuff up. And you can bear it. You can bear to look at the formal stuff. And some might even like it. So the reason, but I want to point out something. So we've got this tiny intermediate language called GIL. So but it's the core of our Gillian platform, and we can write it down precisely because it is so small. And this is, people tend not to, because they're doing very, they're doing a lot of extremely good stuff, getting their stuff out into industry quick. I'm actually sort of recoiled away from that and wanted to go slow because I wanted to understand. And that's just me, given my temperament. So we can write down the formal semantics of our symbolic execution engine. If you want to look at the OCaml implementation that closely follows this formal semantics, you can. So that's just what is in your spirit. And the user inputs basic actions, which are the fundamental interactions between the language and its memory. And I'm going to show you this with JavaScript, so you'll see this at work. And it requires a single additional rule to do this, on top of the basic symbolic execution engine. And then with abstraction, what you need to do is not just identify the basic actions. By basic actions, I mean something like get set a value in memory at a particular location, or a particular location and field. For abstraction, we work with core predicates. Core predicates is just a predicate for saying, I'm after this heap cell here. So this location field with this value. So that's what a core predicate often is. It can get more complicated, but this in spirit is what it is. And associated with it are getter. For each core predicate is a getter and setter function. Now the idea is that you have the whole memory. You've got the bit of the memory that corresponds to the core predicate. By unification, you find that bit, take it out, that's the getter, you're left with the rest of the memory, you do some work, and at some point you set it back in. That's all that's happening. But it's done at the level of abstraction, not at the level of rewrite. And then we've got a bunch of rules, additional rules to cope with abstraction. And what that's doing is calling the function summaries and folding and unfolding these user-defined predicates. So where the real work is you've got these core predicates, but then you have to build up abstractions to get to the place where we would ideally love it if the general developer can work with. So the place where the general developer understands the interface. So in something like JavaScript, it would be the general developers thinking about a basic assignments. It's not going down to the gritty, what does it mean to do get value, set value associated with those internal functions. The last one is bi-abduction, and bi-abduction is extremely simple, and we were really pleased when we found out, when we realized what was going on. So in an operational semantics, or given an implementation, one knows what errors are. If you're wanting to get the value of an address in memory, then if the address in memory is not there, you're going to have an error. And we're very, very cautious about the errors and give a lot of information about errors, so that when the errors are resource errors, not typing errors, but some which can't be fixed, but resource errors such as this cell isn't in the bit of memory you're working with, we can add it and carry on. That's what's going on with bi-abduction. And it's quite subtle, because an error can have many possible fixes, and the tool developer needs to understand this. And we have a single additional rule that you don't need to look at to cope with these fixes. And with this work, we have general correctness results that are parameterized by the memory model. So for example, for the symbolic execution, we need to know that the basic actions are doing the job that they should. And that is, symbolic actions make sense with respect to concrete actions. And if we've got that tiny little lemma, then we've got the general correctness result. For abstraction, we need frame properties. These frame properties come from the separation logic world. And for bi-abduction, we need the fixes make sense. And if we have these, then we have the general correctness result. So now I'm going to show you how to instantiate Gillian with JavaScript. And the reason for doing this is actually because JavaScript memory model is extremely small and extremely easy. So the difficult part of JavaScript is humongous amount of control flow and to cope with different pathways through the standard. So for example, an assignment statement has hundreds of pathways through the standard to say what the assignment statement means. But actually, the interaction between JavaScript and its memory model is very simple. And you can get, I think you'll understand, even though you haven't got you might not know JavaScript. So in the concrete case, we have a location. A heap is given by, is a function where we've got a location and a string. The string corresponds to a property or field, and we get out a value. The memory model consists of the heap, which is fairly normal, a domain table, and metadata table. The domain table is saying what properties or fields are allowed, and the metadata table is giving metadata associated to objects. In the symbolic case, this is very straightforward. We just have symbolic expressions instead of the location, strings, and values. We have symbolic expressions and some condition saying what it means for a heap, a symbolic heap, to be well formed. And it means that the locations have to make sense in the symbolic heap, i.e., they have to be separate from each other. We have just 8 actions for managing the heap, the domain table, and the meta table, so it's small. We also have a compiler from JavaScript to Jill. So what I'm going to do now is just talk about these two, the actions and the compiler in a little bit more detail. Then I'm going to the evaluation. I'm not expecting you to understand this formalism. I'm just trying to get some points across. So here we have get cell with a location and a property string. For this to succeed, we need the cell with the location and the property in the heap. It has a value. And here we are in the success case. When it's not in the heap, it has an error case and an error description. The same thing is going on in the symbolic case, except for we're now dealing with symbolic expressions. So we've got a symbolic location, a symbolic property. It matches a symbolic heap, and it matches in the symbolic heap another symbolic location and another symbolic property. And as long as they are equal, as given by adding a path constraint to already the original path constraint pi, as long as this is satisfiable, then we're in the success case. We might be in more than one success case because the match between this symbolic location and property with the heap might have more than one answer. And then we have the error case as well. With abstraction, the core predicates is just this one, which is a cell assertion. And we have the getter and setter for get cell that frames off and frames on. I'm not going to go through that. For bi-abduction, we fix errors. So when we have a missing object, then we've got, as described here, so given the symbolic location and symbolic property, it's missing, then it can be fixed in 2 ways. Either it has a value in JavaScript is this descriptor, and in the symbolic case, we have a symbolic variable for the value of the property, or the property is absent, and we're using this information to say that it's absent. So we can give these fixes and continue, and that's what the bi-abduction is doing. The compiler, it preserves the memory model and semantics, as I said, I want it to be trustworthy, so I want to follow the standard line by line, so I know exactly what's going on between my compiler and the standard. And I want to test it sort of independently from my analysis and verification world with the official test suite. It passes the applicable tests, bar there's a difference in how we work with strings between OCaml and JavaScript. That's the difference there. We've got big coverage, and we implement the internal functions in GISL. This is for the people specialist on JavaScript. Here's the evaluation. We have the Buckets real world library. An MSc student did the symbolic tests very straightforwardly. And we found some bugs in a library that's used a lot already. And we've got this many lines of this number of Jill commands, and we're in this sort of order for this sort of number of seconds. We also did bounded correctness results. So there's a cache library that's a compact version of jQuery, used a lot. And we extended our work with events. We've done it for JavaScript, but we've done it in a general way, so we'll be able to do it for other things. The number of Jill commands is getting huge, and still we're not doing badly in time. And the sort of things that we can prove is, if a single handler has been registered for a given event, then that's the only handler that can be triggered for that event. And that actually wasn't true. There were 2 bugs. They got fixed when we reported them. But now it is true up to the bound of the input that the length of the event type is of most 20 characters. Finally, the last one, we've done full verification of AWS code, and in particular, the particular message header. And what the code developers at the moment do is write this sort of thing. Element count and fields per element must be non-negative. And so what we've done is turn those comments into our formal predicates, or formal assertions, and done verification on it. It's 170 lines of code. So this is only just right at the beginning of what's possible, and was really hard. This was done by Petter, and it was a hard thing to do. The deserialization module is correct now. In particular, we discovered 1 bug and 1 vulnerability. The vulnerability was to do with a frozen object that should have been frozen and wasn't. So that one was quite a thing. The bug was a bug that we've actually predicted in theory, and we keep on finding in practice, which we very much like. But also, just as importantly, as we were doing this work, we've gone from algorithm and data structure to real world code, and we really had to significantly improve both Gillian and Gillian.js. So this was an enormous learning curve and a great learning curve for us. So this was 2 person months work of concentrated work. This means Petter. And there's a huge number of lines of annotations, but we need to understand this better. So some of this is to do with actually the data structure is really hard. And the annotations are to do with the data structure, not to do with those 170 lines of code. So actually, if it's for the whole library, not for the specific bit of code. But we have to understand, how do we get this down further? And this is my last slide. We need to do much more. So we need to improve our instantiations. We've been doing a lot on Gillian.js. We're on Gillian C. We are improving lots, but I think we're going to end up moving to Rust rather than staying on C. We will see what happens there. Of course, we need to do everything better. We have had MSc students last year and doing error reporting and continuous integration. And we've got another MSc student this year on the error reporting. We really want to get this good and much better than the humongous things we've got at the moment. More languages, definitely Rust. In other work, we're working a lot with WebAssembly, so we do have that as a question mark, whether we will be thinking about WebAssembly. And we always wonder whether or not we should be able to do domain-specific languages. And we always put this up in the hope that somebody will say, oh yeah, you do it on this would be super. And we haven't had that, except for, of course, everybody says, can we do Python, which yes, we can do, but we haven't got the manpower. We're going to do Rust, not Python. And that's more just what we like. Then, of course, we need more analysis. I've got a project funded by Facebook to do incorrectness logic for those of you who know about it. Gillian's going to be perfect for that. It's already on the way, and incorrectness has filled in some bits that we really are very happy with. I know the one I really am interested in is this interoperability. So we've done the AWS code for JavaScript. There is also this AWS code written in C for the same thing. And so what we're on the way to doing is seeing if we can verify the C code, and then how like the specification of JavaScript code and the specification of C code, and where are the points where they really match and where do they not match at all, because there's too much heap complication that's different, and where does the heap complication spill out, so even though it would be nice that they matched, they don't match yet, bother it. That's where we're at the moment. Thank you very much for listening.
Right. Thank you very much for your talk. Right. So do we have questions, please? We've got a couple of questions from QA session, but they were already answered. So we may get
It's going to be very good at
that. So does anybody want to unmute themselves and ask the question? A question?
Can I ask a question?
Please, John.
Hi.
Do you have some examples of what the annotated JavaScript code looks like to get an idea for what it'd be like for a developer, like a normal developer, to start adding annotations like this?
Let me very quickly go there. Just a sec. How do I? If you'd given us an hour, you would have heard the fabulous Petter. The sort of things that we could do is we've got this sort of very, very complicated list. We've got deserialization going on, and in particular, we've got things like these sorts of functions where we have a function decode encryption context that goes to a key value map. So if I go, the sort of things, we just judged that it was too complex to do all this in the half an hour talk. I did try. So in particular, we've got these sorts of assertions. And we end up with this sort of code. So to establish the loop invariant, there's 4 tactics, 27 invariant components. There's to re-establish the loop invariant, there's 9 tactics. And Petter, I don't know whether you would like to say any more.
So hi everyone. I don't quite know who is seeing me, who is not. This is all quite confusing. I seem to be there. So when it comes to verification, the workload is comprehensive. There's a lot to do, and this has to be done by experts. This is nowhere really near the general developer, but the correctness guarantees that you obtain are significant. So actually obtain full correctness guarantees. We do have symbolic testing, which it takes much less of a toll on the developer. So if a developer can write concrete tests, they can probably write symbolic tests. And that is probably the correct place right now for the general developer in the context of Gillian.
And what's very interesting is that Amazon at the moment knows that verification is very hard. But for example, they're very interested either in-house or in bringing academics to interact with them. They were the one that said, can you do this for this amount of code, and gave us the code. So they're wanting to see where the world is and where it might go. And that's what they're exploring at the moment, knowing that it's not there yet, but what happens in 2 years, what happens in 5 years, what happens in 10 years? And what should we do as the Gillian developer to help that pathway from the academic verification to the industry verification? I think this is I do know Pete O'Hearn inside Facebook, he would love to do verification. And at the moment, it's really difficult because given what the way they work, every 6 months, they need to be seen to be delivering. And so the time frame is so short in the context of this verification work. So what can we do to help this along so that when the techniques are ready, they can be scooped up by industry in a way that they can get that quick results in those 6-month periods? So this for me is the real challenge. And if we manage anything like that, we're doing a great job. You know, it's hard. Maybe, or some other colleagues. You know.
Right.
I have a sort of follow-up question, if it's okay.
Yes, please do.
Yeah. So could it be? I'm not sure how these annotations look and what you can express in them, but you were talking about sort of long-term adoption and so on. Could you use these annotations and use them as sort of contracts or something that you could do at one time and then, you know, gradually move to more and more advanced?
Absolutely. So for example, if there was an important library and people were prepared as specialists to do these specifications, then absolutely, what's it mean? How does one check? One can do concrete checks as the program's running, anything like that. Absolutely. Yeah. All of that absolutely applies. It's just given our academic heads, we're not quite going for what is useful now. We're going for where does these techniques lead to? Yeah, so we're in a slightly different question from what's useful now. Whereas there's some academics that do that's their raison d'etre. They really want that. Whereas we're wanting to be a bit slower and not quite going for the jugular. We're going for the jugular in the theoretical, technical sense more than in the be useful now sense.